Okay. Apparently, I'm a little out of touch with rusty with using Zoom, talking over Zoom. So I appreciate those of you who've turned on your camera so I can actually speak to somebody in person. I'm very excited to be here with you. I wish I could be with you guys in person, but I'm going to make this somewhat informal. And listening to the program that you have for Sam, I'm hoping that I'm going to show you how I can touch along a lot of the topics that you guys are also be looking at. So. I come from the formal methods community, but over the years, I've moved into model-driven engineering. And then for the last almost 15, 20 years, I have benefited from looking outside of my normal box and comfort zone and reaching out to different disciplines to help me deal with uncertainty, and uncertainty specifically in the context of autonomous or self-adaptive systems. So today I'm actually going to try and share with you some of the kind of my journey that I got to this point, and looking at some of the early autonomous systems. And then as we now have gone into the second or third coming of AI, depending on your age, they're thinking about how we can now also be looking at uncertainty, but now we also have to look at it through the lens of AI and how it helps us deal with it, and also how it might pose some additional challenges. And as always, I'm looking at it, trying to draw from lots of other disciplines. So as we go along, if you have questions, please feel free to ask. And I'm easier probably to see your hand versus the chat part of it. Okay. All right. So without further ado, this work really is representative from a large body of group of people that I've been working with over the years. And you'll see Eric's name in the green box up there. So lots of amazingly talented students. And then also faculty members that I've worked with over the years from different disciplines. And like Eric mentioned, I've also worked with a number of industry collaborators and also had federal support. So the whole space of high assurance autonomic computing has really been from the perspective of when IBM was looking at how to manage these large server farms. How do we deal with the systems as they're going down potentially? Who wants to be the poor intern who has to go in and reroute traffic and so on? So the objective there was, is there a way that we can make these systems be autonomic in the sense that the system's somehow automatically able to observe and monitor its health internally, and also how it's interacting with the outside, and then be able to then detect any problems and then try to go ahead and heal from them. So at that point, so the idea is it's kind of like the human body, So if we are running, our heart automatically starts to increase its heart rate. If it's warm outside, then we'll automatically sweat without us having to consciously make that happen. So the idea was, can we do that also with computing-based systems? And so thus the notion of autonomic computing. So these systems in general have to be able to operate under lots of uncertain conditions. Some of them might be even with malice in mind. And these systems that we're particularly interested in are those that are safety critical, meaning that if you have an error or have a problem, then bad things can happen. People can become injured, you have loss or damage to property, etc. And so, needless to say, these systems have this incredible need for assurance, right? Even in the face of failures, whether they're hardware failures, software failures, network outages, or even security attacks. So with that, we had a project, a fairly large project from the Office of Naval Research. And this was sort of in parallel to the IBM effort. And here they were looking at, can you even make our systems that previously were deployed with one objective in mind, be able to adapt while in the field and be able to respond to different kinds of uncertainty conditions. And so the focus there was just making sure that we could actually even do this in the first place. So there was a whole bunch of techniques that we developed and languages and so on. And one example of some of these autonomous systems, for example, would be like an intelligent transportation system. We are in Michigan, so the automotive space is kind of where we tend to hang out. And here we're looking at individual entities. The vehicles themselves can have autonomous features, but they themselves are also interacting with the infrastructure, the roadway systems, and so on. So needless to say, the need for assurance becomes extremely important, and also even in the face of malicious attacks, for example. So the key part of this is that we are looking at uncertainty, and the sources of uncertainty can come from the environment, whether they're due to physical conditions, whether roadways, other vehicles, and then there's a human interaction, right? So these could be vehicles, these could be pedestrians, the cyclists, etc. And then even also uncertainty coming from the sensor technology. So a lot of these tend to be cyber-based, computing-based, and this is where we come into play. Whether it's actually on board, or whether it's outward facing with the satellite systems, but even the uncertainty posed by third-party devices. Maybe the vehicle itself is fine, but then once you plug in your Bluetooth device or you're plugging in, any kind of, third-party systems, then that potentially becomes another source of uncertainty. So the challenge is dealing with all these different sources of uncertainty and then the complexity itself, hundreds of thousands of onboard features. And then there's these sort of almost competing factors with respect to making these things perform quickly and fast and efficiently, but also making sure that we have the safety and functionality. So a big part of this challenge is how do we deal with uncertainty? And so back probably almost 15 years ago, the National Science Foundation in the US, they're always trying to get their researchers to do new things and novel things. But at that particular time, they said, okay, we have a big pot of money. You can have access to this pot of money only if you are willing to talk to people that you normally don't talk to. In other words, reach outside of your discipline. And this is really when we were looking at, from the Navy project, we were looking at dealing with the uncertainty for the autonomous systems. And so one of the observations that we made with these autonomous systems was to say, well, we can barely talk about the assurance for non-autonomous systems. How do we dare move into the space of autonomous systems? And one of the a key sort of turning point for our work, and I think that in general the community, was that one of my PhD students and we came up with a conceptual framework. We said, well, maybe when we think about assurance for autonomous systems, can we think about our autonomous systems as in fact being a collection of non-autonomous systems, right? These are just sort of normal systems. But the idea is that these different systems are different configurations of a system, each of which is intended to handle a specific set of uncertainty sources. And so with this collection of non-adaptive systems or non-autonomous systems, then we can connect it with adaptive logic, right? So the idea is that you can sort of decide when your operating context is within a particular set of situations, you would use one configuration. And then if you detect that you actually are in an adverse condition, then maybe you can reconfigure yourself to move to a different autonomous system, a different configuration. So that was actually sort of a turning point for us. And I think for this work, a student, his paper received actually an ICSI Best Paper Award. And then 10 years later, we were actually got a Most Influential Paper Award, honorable mention. But I think the point was that helped us to kind of simplify things a bit. So the key point that we left at that time was to say, okay, now, if we want to how do we find these different non-adaptive systems, all of which would satisfy your original objective, but they might do it in slightly different ways. So then that was when the NSF program was announced, and they said, talk to people that you don't normally talk to. And so one of those people was somebody who just joined us in the area of computational biology. And so I thought, well, he's a nice person, but I normally don't talk to this person. So maybe I can learn something from them. And we made an observation to say, well, a lot of the biological organisms have some of the same characteristics that we would like to see in our system, in our adaptive systems. So kind of a little bit of a preview. If we think about living organisms, they actually have quite an amazing ability to adapt to changing environments. There's sort of two ways that they might adapt. One is what we consider short-term or phenotypic plasticity. I'm not sure if we have any snail experts in the room, but if we do, please speak up if I'm saying something incorrect. But if we have a snail, for example, who has a tooth that they can use for foraging for food, depending on the ocean floor itself, if the ocean floor is actually sandy, then the snail who has a sharp tooth is able to better to kind of get through the sand to be able to find their food sources. On the other hand, if the ocean floor is rocky, a sharp tooth wouldn't actually do very much good. So instead, you might be better off with a little bit more of a nubby tooth. But at the end of the day, whether the tooth itself is sharp or nubby, the DNA of this snail doesn't change. So that's why we call this phenotypic plasticity. It's sort of the outward facing features of the system itself. In contrast, if you think about longer term or genetic evolution, again, if we have any entomologists on board, please feel free to say, let me know. So here we have a leaf mantis. And so if you look here carefully, we have a leaf, but then we also have this insect, this leaf mantis, that if you look at the color and even the shape and even the texture itself is actually quite close to the background of the leaf, right? So this all of the leaf mantises that were, bright yellow or polka dotted or pink, those are all gone, right? So this is literally survival of the fittest. So the resulting leaf mantis, okay, that looks like this, is the result of long-term genetic evolution, right? So the DNA, right, is actually representing the one that has this color and texture. The ones that had the bright colors, those were all, they did not survive. So as a result, what we observe is that a lot of the complex organisms exhibit a lot of traits that we would like to see in our self-adaptive or self-managing systems. So example, things like self-system monitoring, right? Senses, that be able to see what's happening on board, as well as what's around us, right? Like, as I said before, like, if you realize that you are it's hot out, then your body is able to naturally be able to detect that and be able to perspire to release the heat. Reconfiguration, right? As you are undergoing more strenuous tasks, you might actually have some muscle growth, etc. Even self-repair, right? If you cut yourself, then hopefully your blood will clot and be able to stop the bleeding, or tissue healing, if you so on. And then similarly, intrusion detection, right? Our immune systems that we can also detect that there is a foreign entity, a virus, etc. And then how do we come back and fight that? So the question was, can we in fact leverage this evolutionary capability to identify those possible target systems that we want to be able to use as a collection for our autonomous systems? So anytime, I think as academics, anytime we, are exciting to try and think about learning new things, but it's also an investment. And so even though we had access to this pot of money, I'm still a little hesitant. So I thought, well, can this really work? So I had some other colleagues that were part of the Navy project, and they were looking at battery management. And so their question was, can they identify more strategic or more efficient ways to do management of battery power? And so this is an experiment where, if you see this grid, each of the boxes represents an organism, right? And if the box is white, it means the organism is working. And if it's black, it means it's sleeping. So the experiment was to say that for the organisms, this is an evolutionary space, they were given a set of tasks, and if they perform the tasks during the daytime, and this circle here will turn yellow when it's daytime, then they will get rewards. If, on the other hand, when it's nighttime, the idea is that they should sleep. So if the organisms are performing tasks, they don't get any rewards. In other words, there's no overtime pay, if you will, right? And so the hypothesis was that during the daytime, everything should be white on this grid, and during nighttime, they should all be black. So let's see. So as we watch this, we observed an interesting phenomenon, and that is that we found that the organisms were actually all turning on and becoming working right before it became daytime, right? And then definitely when it was nighttime, they were off. So we're thinking, well, wait a minute, we said that specifically that they would only get the rewards if they actually were working during daytime. So evolutionary computing, the beauty of evolutionary computing is that it's code. So we can actually go back and look at the code and see what was really happening at those pre-dawn hours. And so what it turned out was that when we looked at the organisms, they were actually getting everything ready, right? You know, getting all the things lined up so that right when it turned daytime, for example, 8 a.m., the organisms were ready to perform the specific tasks. All right. And this was an evolved behavior, all right, that they discovered that if they wanted to maximize their rewards, they had to be ready to go right at 8 a.m. Right. And so versus, you know, those of us who've been in industry, normally you get to work, you know, you got to get a cup of coffee, you got to go catch up with some colleagues, you know, you might do some check some email, and then it might be 30 minutes or an hour before you actually start working for the day. And so these organisms, you know, when we put them into this, you know, in this environment, they were able to discover that it was better for them to maximize those rewards by being able to start right away. So this was one of those things where, you know, early to bed, early to rise. And that kind of evolved behavior, I thought, you know, we wouldn't have designed that, right? Because it was not intuitive for us. So this was kind of a thing for me to sort of realize maybe this evolutionary computing stuff, maybe there is something to be said for it. So we did a whole series of fun evolutionary computing activities, but one of the things I wanted to share with you is something called Loki. And Loki, the objective of it is most of the people at the time when they were developing these autonomous systems were focusing on how do I build the adaptation capabilities into my system that I'm understudy. But and meanwhile, somehow deal with uncertainty. But this uncertainty thing was kind of this unknown entity, you know, so they sort of, you know, sort of kind of guessed here and there about what kind of uncertainty they might want to handle. Loki, in contrast to all this other work, was saying, let's just explicitly focus on generating or exploring uncertainty, right? What, in fact, are the operating contexts that cause problems for our adaptive systems, right? And so this was something that was kind of, it's complementary to a lot of the autonomous systems work at the time. So the idea was that Loki identifies these different sources of uncertainty and then generates combinations of these different sources to produce operating contexts, but specifically because we didn't know which operating context would cause trouble, we didn't have a fitness function like you might normally see with evolutionary computing. And instead, we said, give us the most diverse operating context, right? In terms of being able to try to see if we can uncover interesting behavior from our systems that we weren't expecting. All right, so this is a way for us to explore the, you know, the effects of sensor uncertainty, environmental conditions, etc. So the way we evaluated the diversity was to see how our adaptive system reacted to these different operating contexts. So we wanted just to see a diverse collection, right, based on the behavior of our autonomous system. So in this particular technique that we used was something called novelty search, right? So here's an example. Here we have an adaptive cruise control system, a system that has two key onboard capabilities, adaptive cruise control and lane keeping. So adaptive cruise control is basically cruise control with radar. So it's able to detect an entity in front of it and then be able to slow down as appropriate and maybe deceleration through throttle control or actually even braking. And then lane keeping is supposed to maintain the vehicle in the center between the lane markings. Sorry. So if it actually deviates or drives outside the lane, then it's going to mitigate and bring it back into the lane. So here we have two cars. My vehicle is the one in the rear, and there's a car in front of me. And so we're driving down the highway and things are fine. And then suddenly the car in front of me decides to slow down. And so what you'll see is that the adaptive cruise control is working and it detects that and it tries to slow down, but the car in front of me slows down too quickly, if you will, so that I'm going to bump into it, right? And then you're going to see that actually causes me to drive out of my lane, and then lane keeping is going to kick in. So let's watch this video and see what happens. So you see here, I'm coming up on it quickly and I bump I bump out, and that's a little bit of a fender bender, but it's okay. I'm outside my lane, but I had to come back in now because the lane mitigation is going to. So this is an example of where we actually have what we call a feature interaction. Both features worked as they were supposed to, right? So the adaptive cruise control detected an obstacle or that was getting too close. It tried to slow down, but it was unfortunately, you can imagine when cars, cut you off, for example, when you're driving. So it was going to have that collision. And so that collision was just enough to bump me outside of my lane. But then the lane keeping kicked in, right? And its objective says, oh, you're outside of your lane. I have to move you back into your lane. And so that coming back into the lane then, in fact, caused a much more serious accident, right? So this obviously was sort of an exaggeration, but the point that we were finding here is that we were able to use Loki to uncover operating contexts that we might not have been able to find if we were just trying to come up with test cases, right? And because at this point you have to be able to generate exactly the right combination of the speed of my vehicle, the speed of a vehicle in front of me, the distance between us, and how far we went off the lane, etc. So there's so many different possible ways that could have manifested. But being able to use Loki and novelty search, we were able to uncover this particular interaction. So this is something where, once we see this, then that information could be, then provided back to the engineers. They can go back and say, well, when we have these systems, we can't be just looking at sort of a silo view. We actually had to be thinking about our systems working in conjunction with other onboard systems. So this is an example where we were able to use Loki to generate uncertainty operating context and be able to find something like a feature interaction. So our purpose here was for the overall project, we looked at this whole notion of evolutionary computing or digital evolution. We could actually generate behavior, and then we can look at the code, and then the human programmer could actually codify it and then put it onto we had some robotic devices, these epochs at the time. We actually even had a student who built a cross compiler because it was just programming code. They were actually built a cross compiler for C cross compiler and then generate the code automatically that could be uploaded to the devices. And my space was really looking at the software side of the modeling side of things. Can we get the evolutionary computing to generate software models? In my case, I was interested in generating state diagrams, right, to describe behavior. And then that then could be given to an automatic code generator that could then be able to upload to the code. So this was just sort of some of the pathways that we went through at the time. But the point of this is that we developed a whole slew of different kinds of assurance techniques for these self-adaptive systems, whether it's on actually generating the adaptive configurations, being able to do verification, including model checking at runtime, testing work. This is where Eric did a lot of his PhD thesis, being able to generate adaptive test cases and also being able to generate adaptive test plans. Also coming up with different specification languages and being able to analyze those. But the key thing to note here is that the assurance techniques that we developed really had this combination of sort of using the formal-based approaches, right, to do formal analysis, but then we were able to supplement and bring in these different search-based techniques. And so you'll see that I'm pretty agnostic, especially even in the space of evolutionary computing. We looked at GAs, multi-objective optimizations, digital evolution, genetic programming, etc. So this was able to help us to address some of the different kinds of challenges that we had trying to address uncertainty for these self-adaptive systems. So that was fun. And then AI happened. And as I said before, it's happening again. And so we had a project from the Air Force looking at trust and resilience systems as specifically focusing on assured autonomy. So here we're looking at now systems that might have, one or more AI components. But again, we're trying to also bring together a number of different kind of disciplinary techniques to help us deal with some of these high assurance critical systems, whether it's the intelligent transportation systems, remote sensing, even cybersecurity and warfare, digital chain supply. So we have the traditional software engineering techniques, model-driven engineering, requirements modeling, right? And then we have a lot of the technologies that we had developed, part of the Navy project, like, for example, our relax language, doing runtime monitoring, and then certainly a lot of the evolutionary computing techniques that we've developed. So all of this to support the overall Explore project. So just as some terminology, so you have the learning enabled components, basically a functional piece of software based on AI technology. So for example, you might have a DNN model for image processing. So it's very specific and very focused. You can have a learning enabled system, right? Where you have a system that has one or more learning enabled components. Then we had the self-adaptive system, right? That we talked about before, that you have the MAPE loop that's managing the adaptation itself. And now we're going to add the learning enabled adaptive system capability to that as well. So in the space, real world uses of AI, we've already seen this, right? We're seeing this, sort of become essentially ubiquitous, right? So AI has been used in healthcare, automotive, finance, you pick it, you name it. I think the one area that we wish that we didn't see so much of it probably is in the classroom. Those of us who are still struggling with trying to figure out a way to manage that use and discourage it so that the students can still do critical thinking. So we also are seeing that there's a futuristic concept of, what we think about how we see the whole notion of driving. So this is actually the future where this is clearly a level 5 or level 4 or level 5 autonomy, right? Where we don't even have steering wheel or pedals. So there's no driver involved. So this actually was from a concept picture from 2012. So it's actually way ahead of its time. But the reality check is that currently what we have instead is that we have these different autonomous features like collision avoidance, lane keeping, blind spot detections, and adaptive cruise control, so on. But the challenges that they face include the roadways, right? Are the infrastructures really ready to support some of these features, right? Communication technologies, and then who's in control? Is the human driver in control? Is it the onboard controllers? And then what happens if you actually are trying to share the control of the vehicle between the human, right? Is there enough of that time for that handoff? So along those lines, we have these ADAS features, right? So blind spot detection, etc. And then we start moving into more and more of towards self-driving, right? So a lot of the early Google car technologies, most of them were LiDAR based, right? But they were, as it wasn't intended to be a commodity vehicle that was used by, for civilians. But the idea is that they also were limited in terms of the speed in which they were driving, right? And so Google car obviously has become Waymo, right? And they still have preserved a lot of the same objectives, right? And so they're still sort of speed control. These are not available for the civilian population to drive. So in parallel, the early Tesla technologies, in contrast to the Google car, was that the vision at the time was to say we want these self-driving capabilities to be accessible by the larger community, the broader community. And one key thing to keep in mind is to make it accessible from the point of cost. So one of a key design decision, if you will, that was made was not to use LiDAR, right, for the detection technology, but in fact to use radar. So autopilot, right, was the sort of the idea to kind of taking a spin off from the airplanes, is that the idea is that it's supposed to be able to initially be able to have adaptive cruise control and lane keeping both working in tandem, right? Sort of like the vehicle that we had before. But the computer-based vision system was, camera-based, and then they had radar. But they say it was not intended to be hands-free driving, right? So that was the original technology. So the question is, are we ready, right? And so if you remember, one of the first highly visible accidents was an accident between a Tesla vehicle and a semi-truck, right? And so the Tesla vehicle was at an intersection and then, or on the highway, and the semi-truck was going to make a left. Excuse me. So, sorry. So the Tesla vehicle picked up on the trailer, the back half of the semi-truck. And because the semi-truck trailer was white, the onboard detection system classified that as sky. So clearly with sky, we don't need to do anything, right? So this is what caused that collision. And so when they went back and studied it, it turns out that when they had the litigation, Tesla was actually absolved of being guilty because at the time they could tell that they had alarms on the steering wheel and the driver did not have their hand on the steering wheel. So they were quite familiar with the Tesla vehicle. So in some sense, they actually almost ignored those alarms, right? And they literally only had about 10 seconds before they realized that the car was not even slowing down. So this particular accident happened in 2016, right? And so the idea was that um, as fancy as the car was saying, we provide adaptive cruise control, we provide lane keeping, but at the end of the day, the driver was supposed to be in charge. So then, question is, well, what in our computing space, as we've seen with the explosion of AI, 1 year is a lot of time for technology to advance. 2 years is even more, and 3 years is definitely a lot of time. So what happened 3 years later? Well, it turned out there was almost an identical accident. Same situation. Tesla vehicle was going one direction. There was a semi truck that was going perpendicular and going to make a left turn. And exactly the same thing happened. The Tesla vehicle picked up on the trailer part of the semi truck. Again, it classified it as sky and it did not slow down, right? And it crashed it. The Tesla vehicle crashed into the semi truck. And so, in fact, when I was first doing the research for this work, I thought that the names of both of the victims started with J and B, and I thought they were the same. They were talking about the same story, but it's actually two different cases of exactly the same scenario. And so you say, well, what has changed in the 3 years between the first accident and the second accident? And it turns out that the only thing that changed was that when you to turn on your car in the Tesla in 2019, there's a window, there's a disclaimer screen that says that the driver is absolutely in charge and responsible for the safe operation of the vehicle, right? And the same thing with the um, user manual. And also in the user manual in fine print on one of the pages of the 200 or 300 page document, there's a line that says, this vehicle does not do well with detecting cross or perpendicular traffic. Now, I don't know about you guys, but I must confess, I may not have read my entire user manual for my vehicle. So this was another case. Again, when they went to litigation, Tesla was absolved of guilt again because the driver ignored the wheel warnings, and the judge decided that they should have been paying attention and detecting the truck. So since that time, this is 2019, there have been a number of other autopilot related accidents. And for a while, Tesla had commercials that said, leave the driving to us, right? And they literally show the driver who has their hands not really on the steering wheel, right? And so since that time, since this accident in 2019, there have been other litigations where the court has filed in favor of the families of the victims because the claim was that there is this at least perception that they're giving to the consumers that this car is self-driving, right? And so, and then from that point of view, Tesla was not held legally liable, but they were held, they won the civil suits. Unfortunately, I mean, it is what it is, and I think that nowadays you can find lots and lots of different webcam or dash cam videos showing very scary situations, and they all involve the autopilot. So my public service announcement for you is please be careful when you're using autopilot, because if you're going to use it at all, there's just a lot to be learned in terms of what the autopilot, the training data. So the training data, if you haven't seen it, it hasn't seen it, so it doesn't really know how to deal with it. So that was Tesla. So this is an equal opportunity. So here's another example of an accident due to self-driving car. This was actually the Uber accident where the Uber was getting ready for a big dog and pony show for their sponsors, and they were on one of their test runs, right? They'd already done 70 some test runs. They have the same route and so on. And as part of getting ready for their test runs, they decided to turn off the warning alarms as well as mitigation because they had a lot of false positives. So they did not want to have those alarms going off during their demonstration the next day. So they turned off the warning signs and they also turned off the mitigation because if there's a false alarm with the warnings, it also was, causing the braking system because they were detecting obstacles that were not there. So this was a case where there was a woman who was walking across the street, basically a highway structure, and she was pushing a bicycle that had a whole bunch of tin cans tied behind it. And it was around 10 p.m. In Tempe, Arizona, I believe. And so this was a case where the Uber vehicle actually hit the bicyclist. She was actually walking though. And they went back. And so initially there was just a lot of speculation, like what happened? Oh, this is telling us that, the AI system are not ready. And then when they went back and looked at the black box for the car, they realized that several things were happening. One is that when the Uber car actually did pick up the bicyclist, but it did not know what to do with it because it didn't classify it as pedestrian. It was thrashing. It was like, is this a pedestrian? Is this a bicyclist? Is this an obstacle? So it kept going back and forth, because the person was crossing not at an intersection. They were jaywalking, right? And so this was very confusing for them. And the other thing is that because they had turned off the alarms, there was no alarm to the safety driver. So the safety driver had no idea that this was happening, that this thrashing was happening. And furthermore, they also had turned off the mitigation. So even if they were thrashing, not being able to classify it as pedestrian or bicyclist, it would have said, okay, whatever it is, there's an obstacle that's getting increasingly closer. So we need to at least brake. But because they had turned off mitigation, they also was no braking. And so by the time the driver noticed it, it was too late and they actually hit the pedestrian. So this was the case where the AI system, maybe they weren't able to classify it, whether it was pedestrian or whether it's a bicyclist, but at least it did pick it up because there was speculation at the beginning. It's, oh, it's because it's nighttime, so it missed it. No, but the AI system actually did pick it up. They just, but the point is that the humans, the decision makers, had turned off the warning and the mitigation. So at the end of the day, if you look at some of these statistics, 400 crashes involving self-driving cars, this is just from one particular year. You look at the statistics, the lion's share of them are going to involve Teslas. And that part of that is because there's just a lot more Teslas out there compared to some of the other makers of these self-driving vehicles. But in general, if those that are fully autonomous, right, where they are not just supposed to have the human driver of record, most those are not serious, right? A lot of it is because the speed is actually quite slow, right? And they're very cautious. They tend to be more conservative in their decision making, right? So at the end of the day, we have to be careful what we wish for, right? So this is one of those things where maybe this was sort of predictive for us, right? So that technology's out there. Here's another example of where we had the Chevy Cruise vehicle. This is, if you see the inside of this, this is a robotaxi they were getting ready to release. And notice how close this robotaxi interior looks to our futuristic concept car that we showed at the very beginning of this that was predicted, more than 15 years ago. But the robotaxi was a collaboration between Chevy Cruise Cruise and also Honda and GM. So here was the Cruise Bolt, and the idea is that they had a license initially from the DMV to drive. They had a safety driver. And it was supposed to be self-driving, right? And then they did so well that they were able to upgrade their license to be able to remove the safety driver, right? And so one thing to note is that most of their test rides when they first started were actually between 10 p.m. and 5:30 a.m., right? And so the idea is that, those are probably the times of day that maybe you won't have as much traffic to deal with. But the exciting thing for the cruise Bolt was that they had developers that were really, really quick and responsive to dealing with assurance concerns. So their sort of protocol was that if the car encountered a situation that they did not know what to do with, their response was to stop the vehicle, right? And so, because from the physics point of view, if you're not moving, you can't hit things. But it turns out that sometimes they stopped at the inopportune times, right? And so that would actually block traffic, all right? So then they changed their protocol to say, all right, when you encounter a situation that you don't know what to do, stop and then slowly pull over to the right-hand side, right? And so when they did that, they ended up similarly when they pulled over, they sort of just pulled over wherever, randomly. But it turns out sometimes they pulled over and were blocking intersections. And that included situations where they were blocking emergency vehicles from being able to cross through. So then they had to modify that instruction or guideline to say, okay, stop, pull over, and make sure you're not blocking an intersection. All right, so and then they had a situation where there was another vehicle driving and there was a pedestrian crossing. Again, the pedestrian was jaywalking, and this other vehicle, not the cruise, but the other vehicle was not expecting that, and they actually hit the pedestrian. And then that other vehicle actually ran off. So this is what we call a hit and run. But anyway, the other vehicle hit the pedestrian so hard that the pedestrian actually took air and then landed right in front of the Chevy Cruze. So if we remember the guidelines for the Chevy Cruze, and that is that when you encounter something, you first stop and then you pull over, not blocking an intersection. So that's what the Cruze did. They stopped when the pedestrian landed in front of the vehicle, and then they pulled over to the side. Unfortunately, because the pedestrian was so close to the Chevy Cruze that when they went to go pull over to the side, they actually ended up dragging the pedestrian some amount of distance. Now, fortunately, the pedestrian survived. So I don't want to have a bad ending in my story here. But so when the Chevy Cruze people went to talk to the DMV, they because DMV is the Department of Motor Vehicles is the one who gave them the license to drive without a driver. They showed them the video, right? And they showed where the pedestrian landed right in front of them and the Chevy Cruze stopped. And that was all that they showed the DMV. And so the DMV said, oh, well, you did your best. There's hardly an avoidable accident. But they didn't show them the rest of the video. But nowadays, everybody has a camera, right, with a phone. So a third party entity had recorded the accident, and then they were the ones who provided the second half of the video, which is when they actually dragged the pedestrian. So they provided that video to the DMV, and that's actually how the Chevy Cruze lost their license to drive without a driver, right? But they could have still continued to drive as long as they had a safety driver. But at that point, the cruise organization, the cruise group, decided that their reputation was so badly damaged that they basically recalled all 950 vehicles from the market. So that's again another situation where there's just the human still has a purpose. Let's put it that way, right? All right, so it just shares that with you. So essentially there's real world consequences, right, in terms of the use of AI. So we are seeing ChatGPT, there's now multiple LLMs out there, and they're being used for lots of different purposes, some of which maybe are not necessarily the most the best, the highest integrity. And so there's a whole notion of trying to police a lot of this. And there was even a big letter, with all of especially including all of the AI experts who said, we need to think about what we're doing with AI and making sure that we're still doing it for good, right? Rather than potentially causing harm to society. But unfortunately, the genie's out of the bottle. It's too late. We literally have to face the music and figure out how we can deal with this technology that we have unleashed. And I think part of this is that now that people are able to use it, and I think the other thing is that the issue with the LLMs is that in contrast to previous pushes for AI, LLMs have made AI accessible to everyone. You don't have to have a PhD, in computer science to use AI now. Everybody can use it. I mean, they can use it for, unfortunately, as we are seeing in the academic world, they can use it for coding, they can use it for their writing, etc. The people in the arts community are worried. So it doesn't require computing expertise to make use of it, right? And I think that this is where it poses lots of challenges for us, especially from the safety critical and autonomous system space. So really there is sort of potentially an interplay between self-adaptive systems and AI. So we've seen, we can think about AI for software engineering versus software engineering for AI versus software engineering for learning enabled self-adaptive systems. All right, so there's been a lot of work. If you look at the software engineering conferences, I think fewer than 10 years ago, we had just a few papers that might have involved AI, and now almost every paper has some degree or some mention of AI. So we've used the AI for testing, analysis, code generation, code optimization. So this is where AI can help us with our software engineering tasks, right? You can and now it seems like I belong to a lot of different communities. I belong to autonomic computing conferences. I go to the models conferences. Software engineering, generic software engineering, requirement engineering. Everybody's got AI, one way or the other. But now, and then we've also even used AI for helping us with self-adaptive systems, right? Figuring out how to come up with the adaptive logic, and you can use AI for that. You can use it for decision making. You can actually use it for actually the configurations themselves. But the question is, what about software engineering for AI and machine learning? Right. So prior to that, it's like, you can, use AI in whatever way you want. It doesn't have to be reproducible. It doesn't have to be, generalizable, etc. So is there a way that we can somehow look at how we can be more rigorous and more systematic about developing our AI-based systems? So there's been different surveys and reviews that have looked at what kinds of factors cause AI systems to fail, right? They tend to be brittle, right? Because they're kind of designed for a specific purpose. And if you deviate from that, right, then that will probably won't work. And something, with like it's based on its training data. If it hasn't seen it before, it doesn't know what to do with it. So, and so it, by definition, it's going to be biased based on what kind of training data it's exposed to. You don't have this notion of explainability. So we can't go back and look and say, well, what actually caused the model to behave in the way it did, right? And we still can't really quantify uncertainty. But the key thing is the heavy reliance on the training data itself, right? And so the training data typically is going to be selected and determined by the humans, right? So that's where you get the bias. And also if there is any misperceptions, that gets passed along to the AI-based systems. So Tim Menzies put together the 5 laws of software engineering for AI, but the key thing is that a lot of it isn't that it's not just about the software AI itself. It's that we need people who have software engineering skills to be helping us to think about how we even developed AI-based software components, right? So if we can practice some of our software engineering skills, then the AI-based systems themselves will then be able to benefit. So Microsoft put together this sort of little process model for how we could try to distinguish what the differences are and the similarities are, right? But at the end of the day, it's really all about the data itself. How can we find more effective ways to collect and manage the different data that we need to expose to our AI-based systems? And is there a way that we can promote modularity, right, between the different AI components themselves? So the challenge question is, what about software engineering for learning-enabled self-adaptive systems? And in the spirit of being multidisciplinary, I would say, what about search-based techniques? Search-based software engineering for learning-enabled self-adaptive systems. And so this is where, again, going back into the space of trying to deal with assurance, we find that one of the key challenges is how do we know how robust our system is with respect to uncertainty, right? Because we can't use a lot of our standard testing techniques, for example, that we would have if we had code-based systems. So we observe, as we said before, that a lot of this is going to be based on data driven. So if you have not useful data, then you get not useful responses, right? And so how can we really focus on the real world uncertainty? So we want a technique, automated techniques that can help us to assess how robust our learning enabled system is to uncertainty. And then maybe we can also generate some underrepresented data, right? So if it's not robust, can we generate some synthetic data to help fill in the gaps? And this is where we have our Inky work. And Inky, Loki was our Norse mischief god, right? To generate operating contexts to explore uncertainty. Enki is a Sumerian mischief god because we're now moving into looking at how we can generate uncertainty conditions for AI-based systems. So the idea is that it's really looking at using evolutionary computing to generate operating contexts, but again, with an eye towards diversity. We really wanted to see what's the widest, broadest range of diverse operating contexts that we can expose to our AI-based systems, right, to see how robust they are. So, for example, we could think about if you have uh, your onboard obstacle detection system, and maybe the training data itself was all picked out when you had clear weather. But what's the impact if I have rain, which happens, and so not what kind of rain drops might cause a problem. Is it going to be how large the raindrop is, how much of the image itself is included, etc. So Inky is looking at how we can evolve different, this is just an example application, but how we can evolve different kinds of instances of rain, whether it's the location on the lens itself, what the opacity of the raindrop it is, and also even the size. And so we could actually generate a diverse collection of different kinds of raindrop conditions to see what kind of behavior or that the onboard classification algorithm might have. And so we were able to generate enough raindrops that we're actually able to definitely cause the system to not behave as expected. So then we can use that to assess how robust our system is with respect to rain in this particular case. We also used it for a bunch of other uncertainty conditions. But then once we are able to generate this synthetic data to assess it, we can also use it to improve the robustness of the system itself, right? So this is a way for us to uncover challenging unknown unknowns, right? And then we can then improve the performance and increase its robustness, right? So that was one way for us to robustify a learning enabled component. So then sometimes what I find with AI-based systems is that I think about it as sort of your arrogant friend who always knows everything about everything. No matter what question you ask them, they always have an answer, even if they really don't know, anything about that particular area. And we see that with a lot of AI-based systems. It always gives you a response, right? Even if the response is not correct, right? We see that with hallucinations, for example, now with chat. So our question was, can we somehow find a way to determine when an AI component is just out of its league? It's outside of the scope, right? It's not able to handle the current operating context. And so this is something where we developed with a technique called Enlil, another Sumerian god. It's more of a decision-making type person. And so here we're trying to say, when are you encountering an operating context for which you are just not able to handle given its current configuration, right? So that so we had this paper called Know What You Know, right? Predicting behavior for learning enabled systems. And so you're trying to figure out what the limitations are for your system. So again, in the context, if we think about driving, and so here I have an object detection technique component where on a clear day, I can pick out the car, I can actually pick out a bicyclist. And then maybe if I have light rain, I can still identify my vehicle and I can still sort of make out my bicyclist. But now when I have heavy rain, I can make out my car, but I've lost my bicyclist, right? And so now that obviously would be a situation where my system on my onboard system needs to know that so that it actually can go into a different mode of operation, whether it means you have to go into fail safe, and realize that the driver has to take over so that they can monitor what's happening out there. So, so what is that threshold of acceptance for the rain itself, right? So know what you know and know what you don't know. So here's an example. Yes.
Sorry to interrupt. We have another talk starting at 9, scheduled for 9:40. So can we, unfortunately,
Oh, okay. All right. I will show this slide and then I can go to my summary slide. How about that?
okay, thank you.
Okay. Thank you. So here's an example for the Enlil's working. And so initially I can pick out I can detect my different obstacles or different objects, and then I can introduce a raindrop. Oh, I'm missing out some of my detectors. But now if I turn on Enlil with my behavior oracle, I can actually detect that there is a raindrop, right? Oracle activated. And then I can see different instances of what's happening. So the yellow is determining, maybe I'm missing only a few objects, and the red is saying you're missing some critical objects that actually might cause your system to, cause an accident, for example. So this is an example of saying, being able to detect these different modes of operating context. So with that, we were able to push this into a modular framework for being able to build our systems so that we can pull these things together. So idea is that we don't want to have just we don't want to have one monolithic system that can actually be used to assess uncertainty. So we can talk about the robustness itself. We can talk about the behavior oracle determining when different instantiations of the system itself is not working. So let me, and that basically led us to a whole series of different kinds of learning enabled assurance techniques that dealt with, again, both with the formal techniques as well as being able to add search-based techniques. So again, the requirements engineering completeness assessments, looking at the assurance cases, and all of these are applicable to those that are AI-based kinds of systems. So here's our current and future work. I'm sorry, here. So my most recent work is looking at human-based interaction as a source of uncertainty and looking at different driving models using gaming theory and probabilistic programming. And we have different types of platforms, small size, 1/5 scale, and actually a full scale autonomous vehicle. So concluding, we have autonomous systems and self-adaptive systems. We address a lot of challenges, but we still have a lot of assurance challenges. Some of the traditional assurance techniques, we've addressed many challenges with different kinds of model checking, testing, etc. But we still have a lot of challenges due to the scale, complexity, uncertainty. And then we have different disciplines that we can really make use of. And this is why my key thing is really being able to leverage some of the techniques coming from these other disciplines. But now we also need to be thinking about some of the non-competing issues, some of the social, behavioral, economic issues. And then with that, we have sort of the open challenges, right? Leveraging the disciplines. And then the to-dos is really, trying to, leverage what we've already learned from the software engineering community for many years and all the oldies but goodies, modularity, reproducibility, reusability, etc. So acknowledge various contributors to this work. And with that, I will take some questions.